Our our presentation title is Proximal Policy Optimization for Large Language Model Fine-Tuning. In this slide, you can see the outline. We talk about main idea, then training process of large language model. We present formulation along with the overview of PPO. Then we talk about the main topic and finally present the references. The main idea, a question has been asked from ChatGPT. Can you explain to me how reinforcement learning with human feedback work for language models? The response is as follows. We have a robot that has a language model and wants to start talking, learn how to talk. We have a human supervisor. This robot generates some output, generates some sentence, and human supervisor give it some feedback, and then robot evaluates its works. And this process, trial and error, is repeated until this robot learn to properly talk. Over time, this robot will learn how to talk with a human thanks to the feedback he received from human. This is how language model can be improved using reinforcement learning with human feedback. Okay, overall, the training process of large language model has three steps. We have a pre-training step in which we pre-train a language model. We have an initial language model that can be used to generate text. Then we gather data and train a reward model, a preference model that takes in any text and assign it a score of how well human perceive it. Preference model receive as input a text and give it a score how it is good. And we finally we fine tune the language model with the proximal policy optimization. PPO is used to optimize the original language model with respect to the reward model. Uh, Here I have provided a formulation like any deep reinforcement learning solution. We provide MDP formulation. You can think this as a MDP for LLM. We have an observation or a status space. Or observation space is the distribution of possible input token sequence and or action spaces, all the token corresponding to the vocabulary of the language model. You can see that and you can notice that our observation space and action space are very large. A state space is the distribution of possible input token sequence, and action space is all the token corresponding to the vocabulary of language model. Also, our reward function is a combination of the preference model and a constraint on the policy shift that I will talk about it. Okay, and policy is a language model that take in a prompt and return a sequence of text. The objective is that we repeat this process of trial and error until we learn an optimal policy, a good language model. What solution do you use for this formulation? As I discussed it, we have a very large, extremely large observation space and action space, and we have to use a deep reinforcement learning solution. Okay, because our state and action space is large, extremely large, we use proximal policy optimization to solve this formulation. But what is the main idea of the proximal policy optimization? Look at this PPO. We have a is a policy gradient approach. We optimize directly the policy. Okay, we seek for a policy improvement that doesn't cause performance loss. We want to find the best policy improvement that doesn't decline the performance. This is the main idea of the PPO. We have two versions of the PPO. PPO penalty and PPO clip. In PPO penalty, we compute a KL divergence that I will talk about it and use this KL divergence in the objective function. But in the PPO clip, we don't have a KL divergence term in the objective and doesn't have a constraint at all. Okay. The version of PPO that is used in the large language model is the PPO penalty. Um, Two facts about PPO. PPO is an on-policy algorithm. What does mean? We have two type of algorithm in deep reinforcement learning: on-policy and off-policy. In on-policy, we use data related to the current round of the operation. We use the current data. We use the present data, and then do the operation. But in off-policy, we use the past data. We have a memory and we retrieve data from the memory uh, and then do our operation. But in on policy, we just use the current data, present data. PPO can be used for environment with either discrete or continuous action space. I have presented a paper in ITRP transaction on vehicular technology that for the first time in literature, we combine discrete and continuous action together and present the joint optimization. I will provide link in the end of the presentation. Okay, here we try to provide a better understanding of the PPO. We have a rollout buffer, first of all, in the proximal policy optimization. In deep reinforcement learning, for example, in deep network, we have an experience reply that is used to store the past data. As I told you, PPO is the on-policy algorithm to use data related to the current round of operation. We store this data in the rollout buffer. As you can see here, we have a query. We give it to the language model and generate a response. We have evaluation step. We give query and response to the reward model to evaluate how good is this combination and assign it a number. And then we go into the optimization step. We provide query plus response as the input to the reference model. This reference model is the one that first we use in the first step of our work in fine tuning is the initial model actually, and this active model we obtain it after fine tuning, supervised fine tuning, and we work on this and we call it active model. Okay, the idea is that after providing input and receiving feedback, it generates the log probability. But what is this log probability? See, when we code the PPO in Python, we use log probability to represent the policy for the PPO. Okay, it means we update the policy here for the active model. We compute the change in the policy for the active model and also change in the policy for the reference model. Then compute the ratio and give it to KL divergence to understand how much this new policy generated by active model deviate from the current policy, and along with the reward we give it to the optimizer and it gives feedback to the active model, and this process is repeated. In this figure, we look at the problem from another perspective. We have, as I told, we have an initial language model. We have tuned language model. We provide some prompt. For example, a question has been asked here. A dog is the initial language model says that a dog is a furry mammal, and the tuned language model said is the man's best friend. Okay, we compute the change in the policy for both of them and pass them to the KL divergence to compute deviation of the new policy from the current policy, and then this we compute the KL divergence and plus to this reward. we give it to the optimizer to update the gradient and update the active model. And this is the reference. I use some post from Hugging Face and OpenAI, and also you can see the name of my paper accepted in TVT. And if you want to a version of this paper, you can send me an email. Thank you very much.